Hello everyone. So today's topic is backtracking, anchoring problem, sum of subsets. So the contents are introduction to anchoring problem, 4 queen problem using backtracking, 8 queen problem using backtracking, sum of subset problem, and example of sum of subset problem. Okay, that we'll see with the help of backtracking. So what is anchoring problem is? So basically we have n cross n chessboard. Okay, so in this n cross n chessboard we are asked to place n queens so that no two queens are in the same row or in the same column or in the diagonally. Otherwise they will attack each other. So for n equal to 1, the problem has a trivial solution, and there is no solution exists for n equal to 2 and n equal to 3. Okay, so let's first discuss 4 queen problem, and then it will be generated, or we can generalize it for n queen problem. Okay, so here we have a 4 cross 4 chessboard. That means we have 4 queens, and we have to place these 4 queens in this chessboard. Okay, so let's take the 4 queens. So we have 4 queens. We have queen 1. Okay, we have queen 2, queen 3, and queen 4. Okay, so we are placing the each queen queen 1 in row 1, and queen 2 in row 2, queen 3 in row 3, and queen 4 in row 4, like this. So this is our task. So we are placing the queen in row wise. Okay, so that they are not in the same row, column, or diagonal with each other. So this is our task. Let's see how many solution does exist for this problem. Then we'll have next questions on 8 queen problem. Okay, so first we'll draw this stack space tree. This will tell us how many possible solutions do we have for this problem. Okay, now so let us draw. So suppose this is our first queen, that is our queen 1. Okay, so this is our first queen. So uh, this queen is placed in the first column. So I am placing the queen 1 in the first column. Okay, so queen 1 is placed in the first column. Okay, now listen. For what is the next options for queen 2? So queen 2, let's place in the second column. So it is our x2. So in the second column I am placing the queen 2. So let us place this queen 2 in the second column. So here you can see queen 1 and queen 2 are diagonal with each other, so they will attack. So this is not possible, placing queen 2 in the second column. Okay, let's so this is our bounding condition, so we don't consider this one. Okay, so we go, this is our dead end, we can say, for backtracking. Now come back again to second, this queen 2. Let's place this queen 3 in the third column. So let's see what is the possibility. If we place the queen 2 in the third column, yeah, we can place, we have space. Let's try to place the queen 3 now. So queen 3 can be placed in, let's place in the that is second column. Okay, so if we place queen 3 in the second column, now queen 2 and 3 will attack each other, so it is not the possible. So we have to shift. The next choice is only queen, that is fourth column for queen 3. Okay, q3. So it is our dead end. Again backtrack. Now let's the next option is place this at the fourth column. So fourth column means this one. Okay, here you can see again this q2 and q3 are diagonally adjacent to each other, so they will attack. So this is also not the case for q3. Now you can see there is no space left for queen 3, so that means we are not able to place queen 3. So since we are not able to place queen 3, so placing queen 4 is also not possible. So this is also dead end. Okay, so bounding condition, this is a bounding condition. Okay, now again that means now we have to shift the queen 2 to the fourth column. Let's see. Now we are shifting this to the fourth column. Okay, second queen. Let's shift to the fourth column here. Fourth column, this one. Okay, so let's erase this one so that our diagram will be clear. Let's erase this. Okay, so just for a better understanding, let's erase this one also. Okay, so now our q2 is at fourth column. Okay, now so start. Now so we have placed queen 2 in the fourth column successfully. Let's place the queen 3. So what is the possibility for queen 3? Can we place in the second column? See, queen 3. Yes, we can place, because neither in the same row nor column nor Okay, this condition is satisfied. Okay, now after placing queen 3 in the second column, so can we place queen 4? Where does we can place queen 4? So we can place only left is third, है ना? So let's place queen 4 here. So if you place queen 4 here, so that means it will be diagonal with each other. Okay, so if you place queen 4 here, that means it will diagonal, no space left. If you try to place queen 4 in the fourth this column, again q2 will be attacked. So that means there is no option for q4. So that means this is a dead end. So again backtrack to this one. Let's try to shift the third, that is q3, to the third column. Let's try to shift. Let's see, is there any possibility if we shift to third column? So shift this to the third column, that is q3 will be redirected to the third column. Okay, so again that means we have to erase this one. So now our updated q3 queen 3 is at our third column. Okay, so erase this one. Yeah, so okay, now check what is the possibility, since we can say again q3 and q2 are adjacent to each other, so it is also dead end, so we can't place queen 4. Okay, so queen 3 is also dead end. Okay, so that means again all the possibilities of q2 had been we have traced, so there is no possible q2 now. So that means q3 and q4 also cannot be placed now. Okay, now the only solution is now shift this queen 1. Now shift this queen 1 to the second, that is now we are shifting the queen 1 to the second column. So this is the next solution we can say. So let's remove all this here. It is not even, so let's erase this. Okay, that means now we are shifting queen 1 to the second column. Okay, now since we are shifting this to the second column, this is our queen 1. Now let's see, so can we place queen 2 in first column? See, no, we can't place, because if you place queen 2 here, so it will diagonal, so it is a dead end. Again backtrack. So the next possibility is, can we place queen 2 in the third column? See, no, again not possible. If you place queen 3 here, that is 1 and 3 will be adjacent, diagonally adjacent. Okay, that is not also the dead end we can say. So the only next is, can we place queen 2 in the fourth column? Yes, we can place. Okay, there is, since q1 and q4 they are not in the same row, not in the same row, not in the same column, or not diagonally each other. So this is there. Now try to place, next is queen 2. So we are sorry, it is queen 2. Okay, sorry, it was queen 2, not queen 4. It was queen 2. So it is this one. It was not queen 2, it was queen 1. Okay, so again rewrite this. So queen 1 here, queen 2 here. Now we are trying to place this one, queen 3. Let's see, can we place in the first column? See, queen 3, yes, we can place. So there is no attacking from any other queen. Yes, it is allowed, we can do that. Okay, let's try to place queen 4. Can we place queen 4 in the third column? See, queen 4, yes, I think this is done. So we got, this is the solution. So here you can see neither of the these queens are in the same row or same column or in the diagonally. So we have found one solution, you can say. So okay, since we have 2 more left, so also you can try for this one, that is for your when q1 in the third column, you can try when the q1 in the third column. Okay, when q1 in the third column, and similarly you can try for q1 in the fourth column. So we'll get a huge stack space tree, and similarly you can find one more solution. So here the solution that we have got, is let's draw one array, okay, to store the result. So here it is 1 2 3 4. So total we have 4 queens. Okay, 4 queens, and queen 1 is placed at the second column, queen 2 in the fourth column, queen 3 the first column, and the queen 4 in the third column. So 2 4 1 3 is our first solution. So Can we find one more solution for this 4-pin problem? Yes. So the shortcut we can say directly, if you complete this tree, you will get one more solution. But directly also you can write, just take the mirror image of this. Just take the mirror image. Okay. If you take the mirror image means, so it is this. It is our 4 cross 4. Okay. So it is our first row, second row, third one, fourth row, first column, second column, third column, and fourth column. Okay. So it is a 1, 2, 3, 4, 1, 2, 3, and 4. Okay. So mirror image means, so Q1 is at second column, so make it at third. Q2 at fourth column, just make it reverse, so it will come here. Q3 is here, so make it just reverse, so it will become here. And Q4 will be here. So you can see it is also one more solution. Neither of the queens are in the same row or same column or diagonal with each other. So this is also one solution. So the next solution that we have got, this solution is solution number 1. So next solution is 1, 2, 3. Okay, this is 1, 2, 3, and 4. So queen 1 in the third column, queen 2 first column, queen 3 fourth column, and queen 4 second column. So 3, 1, 4, 2. It's also the next solution. So this is how we are using the backtracking. Okay, for finding the solution for 4-pin problems. Okay, so we have two solutions for this problem. Okay, now the same stack space I have shown in with the help of tables, where we have drawn each chessboard configuration again and again to find the correct solution. Okay, so in the next slide you can see, so it is there are all 7 to 8 steps. So you can see all this all step I have discussed in the stack space only. This also you can easily guess the answer. So finally one solution we got was 2, 4, 1, 3. Okay, now since we have solved this 4-pin problem, so solving 8-pin problem is not that much difficult. Similarly, we have 8 cross 8 chessboard, and we are asked to place 8 queens so that no queen attack another queen. Okay, so that means no two queens are in the same rows or column or diagonal. So if you draw this stack space tree, it will become very huge diagram. Okay, you can try it yourself. Okay, you can find the solution. So there are 12 unique solutions exist for this problem. Okay, since 4-pin problem has 2 solutions, 8-pin problem has 12 unique solutions that you can try for. So this is one sample solution out of this 12. We have placed all 8 queens. Here you can see it is a 8 cross 8 chessboard. It is a 8 cross 8 chessboard. There are 8 rows and 8 columns, and we have placed all 8 queens in such a way that neither of the queens are in the attacking, okay, which another queen. This is one sample solution. So next problem that has the application of backtracking is called sum of subset problem. So it's also a very interesting concept. So what does this concept means? We have some set of integers, we can say some weights, we can say weight. Okay, and we have a sum. That means we have one integer value m, and that's called we can say total weight. We can say just the weight that we want to find for equality. Okay, so the sum of subset problem is nothing but to find a subset from a given set where each element of the set that we have taken of n positive integers in such a manner that all that we are picking the subset will be from the main set only, and the sum of elements of each subset that we are finding must be equal to the some given integer m. Okay, so that means we are finding the subset from a given set, and that subset must equal to the sum of a given integer m. Okay, let's try to solve this problem using backtracking approach. Now for this let's first draw the stack space tree. Okay, then this will give us more clarity of this question. Okay, so the solution, let's take the question. So the question is so here let's take the question. Okay, so let's take suppose we have, I'm writing here only. Okay, here you can write. Okay, so let's take the x as, let's take x as 3, 4, 5, 6. Okay, 3, 4, 5, 6. We have 4 elements, and the value of m is 9. That means we have to find the subset whose sum is 9. Okay, we have to find the subset whose sum is 9. So how to find? So since we know there are two subsets for this given set, if you add 3 and 6 we will get 9. If you add 4 and 5 we will get 9. So let's try to use backtracking approach, and let's draw the state space tree. Okay, so how to draw? So listen here. So basically here what we are doing means, actually what we are doing, we are from a given root node, we are simply uh, including or excluding the weight of the given. So the left one will take 1, that means include. Right one child will take as 0, that means we are excluding that weight. Similarly for this also, include that weight or exclude the given weight. Or again for this this include or exclude, like this. So like this we are forming it space tree. Okay, so let's see how this works with our question. Left child means include the weight, or right child means just exclude the weight. So let's solve this for this given question. So I'm going to erase this. Okay, it is our, simply erase this one. Okay, let's erase this. So we have this set of four elements. Okay, so let's write now. So start, this is our root node. Okay, so in this root node, initially we are taking the sum as 0, that is weightage 0. First add all elements. So all elements sum, it is here 18. Okay, so you can see 6 plus 4 is 10, 10 plus 15, 5 15 plus 3 is 18. Now on the left means we are including, here you can see it is our first, second, third and fourth element. Okay, so just it means x1 equal to 1 means we are just including the 1. So if you include the 1, the weight will become 3. Yes or no? Because 3 plus 0 is 3. Then decrease this sum, so it will become here 15. Okay, now similarly we have 0 also, that we will draw afterwards. Okay, let's again complete this. Now again for x2, let's include x2 means let's include 4. Here x1 is 3, x2 is 4, similarly x3 is 5 and x4 is 6. Let's include 4. If you include 4, the total weight will become 7, and this sum, subtract this sum, so it will become 11. Okay, now again since 7 is less than 9, so again we can go ahead. So let's try to include next element, so see what happens. Let's include the third element, that is 5. If you add this, 7 plus 5 is 12. Okay, and 11 minus 5 is 6. So here you can see 12 is greater than 9. Okay, since we have the total m value is 9, so it is our dead end. So it is our dead end. Okay, so this can't be greater. Okay, we have to find the weight in such a way that it should be equal to or less than 9. So again backtrack, again exclude. Let's see what happens if we exclude the weight. Exclude means we are not adding, so it will become 7 only, and it will become 6. Now try to add the next element. Here it is x3 equal to 0 means we are not including the x3. Okay, x4 equal to 1. x4 equal to 1 means let's try to include the fourth element weight. Okay, that is 6. It will become, okay, 13. It will become 0. Okay, now here you can see 13 is greater than 9, so again it is our end, so it is just neglect. So it's a bounding condition, we can say. Okay, so again traverse back. Let's see what happens if you don't include the x4, that is 6. So it will become 7 only. Now it will become 6. Since you can see here, since 7 is less than 9, but we have taken all 4 elements, x1, x2, x3, x4. That means no element left, all weight over. You can see all weights are over. We are not left with any element to add. So that means again we got the boundary condition here. So again traverse back. Now traverse back to where? To this one, because we have taken all the cases for this. Okay, now traverse back to this one. So here you can see if I write, okay, so let's don't include. So x2 equal to 0 means x2 equal to 0 means we are not including x2 weight. Okay, so simply it will become 3 only, but this sum of total weight, it will become 11. Now again for this we have that is x3 equal to 1. Let's include the third weight, that is 5. So if you add here, it will become 3 plus 5 is 8. Okay, and 11 minus 5, that becomes 6. Since 8 is less than 9, that is, we have again possibility. Let's see what happens. Okay, let's include the fourth weight, x4 equal to 1. If you include the fourth weight, it will become 6. 8 plus 6 is 14. Here you can say 14 is greater than 9. So again it is a boundary condition. Okay, so we have to, it can't be greater than 9. We have to find the subset such that its sum should be 9. So that means again let's check for if you don't include the fourth weight. Let's see what happens. So it will become 8 only, but it will become here that is 0. Since 8 is less than 9, but we have not reached 9, and all elements are over. So again we got the bounding condition. So again come back to here. So let's see what happens here. I think here we will get the solution. Let's see what happens if you don't include the x3. Okay, so you can see we are drawing the left tree only. Okay, so there can be a right tree also for this, for root. If you don't include this x3, so what will happen? The weight will become 3 only, and this sum it will become 6. So since 3 is less than 9, so again we have the possibility. Let's include the fourth weight. Fourth weight is 6. What is 6? 6 plus 3, it's 9. So here you can see we got the 9. So this is our first solution. So we got the solution here. So what is the solution means? 1 0 0 1. So you can see the solution that we have got. I'm writing here. Okay, inside. Solution that we have got is 1 0 0 1. It means 1 means include 3 and last one include 6. Simply add this, you can see we got 9 as the answer. Okay, now if you complete this space tree diagram, so you will get on the right subtree of this one here also if you complete this. Okay, here you can see again if you don't include, you don't get anything, I think. Okay, if you, let's see, if you don't include x4 0, so let's see what will happen. So it will become 3 only, but total weight is 3, but we have used all elements, so again it is a dead end. So that means again we have to come back to here, and we'll draw the space tree. That is, if you don't include the first element like this. So if you complete this rightmost also, you will get one more solution, that is 4 plus 5. So if you complete the right one, so what you will get means you will get like this. So you will get 0 1 1 and 0. So that means just add 4 and 5. So you will get 9 answers. So we got two solutions. So there are two subsets. The first subset is 3, 6, and the second subset is 4, 5. So these two are the subsets for this given question. Okay, so that the m value is 9. So remember here we have used the boundary condition. I have not completely drawn this diagram. This you can do also for x1 equal to 0. Okay, so this is the boundary condition. So total weight, actually it is wxi. So it is like this. Total weight of every till we are using for wi or xi plus weight of this element, it should be less than equal to 9, less than equal to m. If it is condition satisfied, that means our we have reached to the bounding condition. Okay, so this might be always less than, it must be always less than m only. And the second condition is, in some case it may happen that all the elements are exhausted, we have used, and still we are not reaches to the sum m value. So that is this one. Since that is from I to k, all weights for all xi's we have added, and we have used all we have used all elements weight. Still it is if it is greater than m means, that means this is also bounding condition for us. So there are two bounding conditions. So it is bounding condition number 1 this bounding condition number 2. If you see in the previous example where this bounding condition appeared, means here you can see this one is a bounding condition 1, okay, that we have discussed, and here this one, this case, so it is a bounding condition number 2 where we have got 7 less than m, but we have used all elements, okay, we can't reach 9, but here total weight is greater than 9. So these two are the bounding conditions that we have used. Okay, so this is the thing. Okay, so thank you so much.